Buildings, such as homes, offices, and industrial plants, make up the largest energy-consuming sector in the world. In recent years, zero-carbon buildings have attracted much attention in many countries because they are considered an important way to reduce energy bills and greenhouse gas emissions by achieving high-performance energy efficiency. In the following presentation, Professor Michael Leung shares his research with us. Professor Leung teamed up with 12 professors from different universities to develop energy-efficient technology solutions for buildings. Let's see how this works.
First of all, I'm very glad to have this opportunity to share with you about our research. Today, I would like to talk about, we all talk about green buildings. Okay, I will focus more on energy for achieving zero carbon in green buildings. My presentation outline include mainly about building energy efficiency, how we can apply renewable energy technologies in buildings that will include hydrogen energy. Okay, so this is a background information. The International Energy Agency has conducted many studies. Here is what they find. This is the projected carbon emission for coming decades. And the IEA also evaluates different strategies for cutting carbon. Okay, here is the summary. What we should do to reduce our carbon and use energy efficiency. This will contribute a lot. Another one is renewable energy. Also, we can achieve significant carbon reduction. There are other strategies, but these are the two major things we should do. Then further, what we can do in terms of energy efficiency and renewable energies for buildings. Today we talk more about buildings. So part one is about building energy efficiency. And then another background information. This is the statistics for Hong Kong from EMSD. This is about energy end use. So if you look at this chart, you can easily identify that most of our energy, okay, for buildings is consumed for air conditioning. We also consume a lot of energy for heating that include cooking and also for hot water. Most of our energy is consumed for the thermal applications. Okay, then we can further narrow down the scope for developing effective energy saving or energy efficient technologies. Okay, then for air conditioning, so here is also some numbers. This is how much energy, how much electricity we consume for air conditioning in Hong Kong. In fact, this number can be also applied for other cities. Okay, here we have number for Hong Kong. But when we operate our air conditioning system, we have to reject heat to the ambient. Okay, we reject heat. In terms of kilowatt hours, we reject 55 billion kilowatt hour heat to the ambient environment. Then we have this concept. Well, this energy is waste. Am I able to capture this energy to make it useful energy? So starting with this concept, if we further consider if heat is available, of course, then if I use it for heating, then I can turn the waste energy into useful form. We can produce hot water. We can do it for something for preheating. However, when I review our energy demand, we don't really need that much heating. If you consider a hotel, a commercial building, the ratio between air conditioning and water heating is 9:1. That means if I recover enough heat, I still have a lot of waste heat. Then we find out another possible way to use the heat is to use it to produce electricity. If we produce electricity, of course, it can be useful. So in our ongoing project, we team up with 12 professors from different universities, including myself. This is an ITF project. The objective is to convert low temperature waste heat into another useful form. One is electricity. The other one is produce additional cooling. So we have 4 major technologies to develop in this project. This project is coming to the end. So we have already developed these technologies. Number 1 is a low temperature organic Rankine cycle. Well, organic Rankine cycle is well known in power generation. We heat up water to run turbines. In this system, the organic Rankine cycle, we work, instead of water, we work with refrigerants. so that low temperature, we're talking about 60 degrees Celsius heat. This is very low temperature. We attempt to convert this heat into mechanical power. So here is the result. We managed to convert 1.7 to 2.5% of this waste heat into power. You may think this is very low, but if I refer back to the previous slides, we have so much. In fact, this is what we have a lot, low temperature heat. If you can convert 1%, it's very significant. Okay, then we move on to other technology. Well, this is our schematic diagram and our experimental setup. Okay, to move on, if we want to further improve the performance of the organic Rankine cycle, we find out that we need to improve the performance of our heat exchangers. We really have to push to the limit. We have to try to squeeze even 1% of energy output we want to obtain it. So my colleagues, Dr. Edwin Cho is the same person who developed the radiative coating mentioned by Professor Andrew Leung as well as engineer Eric Pan. He is in our team. He developed a surface called biophilic surface. That means the surface it has both superhydrophobic as well as superhydrophilic properties. So here it's showing that when water vapor is cooled and condensed onto the surface, it forms droplets, and these droplets can bounce up due to the surface tension. So this phenomenon, in fact, will help increase the heat transfer for a condenser. So we developed this technology to improve our organic Rankine cycle performance. These are more details about this research. Okay, another technologies. This is the Rash thermal charging cell developed by Dr. Tony Fang from the University of Hong Kong. The application is similar to thermoelectric. When we have heat, we can convert the heat into electricity. So the material is graphene oxide modified with platinum nanoparticles for the cathode, and for the anode is another organic compounds. So when this material is heated, okay, we don't need high temperature, low temperature, even 30 degrees Celsius. We can store electricity in this material. So Dr. Fan is in our team, and he developed this material. Well, in fact, he won a lot of prizes from these technologies. Here is our applications, our target applications. We apply this to collect heat from compressor. Okay, these are compressors used in our air conditioning system, okay, chiller, okay, or refrigeration system. If we attach this material onto the compressor, the heat will charge up the materials and store electricity. Okay, so if I go back to the previous slides, it shows this system can perform this energy conversion or waste heat recovery at 3.5 to 5%. Okay, you may think it is low, but this is still very useful. This is what we need to do. We try to convert as much waste heat into useful form of energy as much as possible. Okay, another technology, this is the absorption cooling technology. This is showing that this is our conventional refrigeration cycle. And we design an absorption cycle to integrate it with our vapor compression cycle. And the purpose of this absorption cycle is to make use of the heat rejected by the condenser. And this will produce additional cooling. When we have additional cooling, that means we have a better higher COP for the overall systems. And in this research, we managed to improve our COP by 6.5%. And the work is mainly done by Dr. Square Fong of the City University of Hong Kong. In this research, we also developed the system. We also developed a very effective absorbent material based on MOF, metal organic framework. So this is another important research development in this research. Okay, then this is also related to energy efficiency. In fact, engineer Eric Pang and Professor Andrew Leung also mentioned this technology before in their presentations. This is the work done by Dr. Edwin Cho from CTU. It's really my colleague. We are from the same department, the School of Energy and Environment. So I may not spend much time, but what the coating he developed can effectively reject heat from the surface to space. But at the same time, it will not absorb any solar radiation. So you have seen this diagram earlier. Maybe I show you another diagram. Here it illustrates how it can be applied effectively This coating on roof can reject heat effectively, so that is cooling, performing a cooling effect, radiative cooling. And this cooling can be used to cool air. Then when we circulate air inside the building, we have air conditioning. Okay, this is an air conditioning system with no refrigerant, with no moving part, well, except a fan, but there's no refrigeration cycle. This technology could be commercialized. We believe there's a very high commercial values for this technology. Okay, next, well, those are the exciting research done for energy efficiency. But still, if we really want to achieve a zero carbon, our energy should come from a clean source, zero carbon or renewable energy. Okay, renewable energy, solar energy has a lot of potential applications in buildings. This is a chart, well-known chart, produced by NREL, the National Renewable Energy Laboratory in the US. It summarized the performance of different types of photovoltaic cells. My colleagues worked with some of the cells, not at the highest performance. Okay, this is about nearly 50% energy conversion efficiency from sunlight to electricity. Down to here is around 15 to 20% efficiency. That includes some latest development of perovskite solar cell as well as quantum dot solar cells. My colleagues, Dr. Sam Su, developed this technology for building integrated photovoltaics. So he can apply this material onto glass panels for windows of buildings. So for example, he studied this glass panels to work with liquid junction solar cell. And then later, he developed technology for such applications. These are vertical windows. At the same time, they are solar cell. The type of solar cell is dye-sensitized solar cell and quantum dot solar cells. And he managed to achieve very high efficiency, 20% efficiency. He also made use of the photovoltaic materials to develop smart windows. There's windows that can, as earlier Professor Andrew Leung said, the windows can be clear windows, it can be tint. This is based on the temperature of the environment. When you change the properties of the windows, you can regulate the heat gain into the building through windows. Okay, besides energy conversion, we also need to develop energy storage technology because if you want to use renewable energy is intermittent. When the sun is not available, we need to store the energy. A battery is one of the popular type of energy storage. Today, we use a lot of lithium-ion batteries, but it is not the best technology. A sink air is safer, is more durable, is a better commercial product. Professor Leung from the Hong Kong Polytechnic Universities, he developed technology for sink air batteries. He developed different types of sink air batteries. He also developed battery that is flexible. When it is flexible, you have a lot more applications. You can apply it for wearable applications. Okay, Leung also developed other technologies. This is a solid oxide fuel cell. Fuel cell is similar to battery. It also converts a fuel directly into electricity. Often we work with hydrogen with fuel cells. Then hydrogen here, I would like to also do a little bit promotion. Recently, Hong Kong IE Transaction published a theme issues on hydrogen power. This is the June issue. If you are interested in it, there are a number of articles related to hydrogen power. And hydrogen is already commercialized. We have a fuel cell in kilowatts to megawatts capacity for buildings applications. We have all the major automakers already have their fuel cell car prototypes ready for the market. Another colleague, Dr. Yunhao Ng, he has developed a nanomaterials photocatalyst to mimic the bio process, the photosynthesis, mimic biophotosynthesis. And this process can decompose water and produce hydrogen. And I also work on hydrogen research. Instead of produce hydrogen, I developed technology that can produce ammonia, which is hydrogen-rich. The advantage of ammonia is that it is not a gas. It is a liquid at standard conditions. Therefore, you don't have to worry about any storage problems about fuel gas. Okay, this is probably the last slide. I also work on this photocatalytic fuel cell technologies. And the advantage of this system is that you can apply it to treat wastewater. When wastewater is treated, electricity will be produced. I would consider that this is free electricity. So all this technology can improve our energy supply and demand, improve our building performance towards zero carbon. So this is our zero carbon sustainable future. our vision. Everything is powered by renewable energy, and hydrogen is the medium. And when we convert hydrogen into electricity, everything is clean. Okay, so finally, I would like to acknowledge the funding I received, especially the 2 ITF projects. And also, I would like to acknowledge my research team that includes all the professors and their work mentioned in this presentation. Thank you.